Hey everyone, welcome back to the channel. Today we are diving into one of the strangest mysteries in modern physics, why black holes still haunt our best theories of the universe. If you enjoy videos like this, please remember to like the video, subscribe, and share it with a friend who loves space and science. It really helps the channel grow, and I appreciate it a lot. I am also curious, what time are you watching this and where in the world are you right now? Let me know in the comments below. Thank you so much for being here, and now, let's begin. At the center of the Milky Way galaxy, in a crowded region of stars and gas, an object called Sagittarius, a star, quietly dominates the local cosmos. It sits about 26,000 light-years from Earth and carries the mass of roughly 4 million suns. Yet in visible light it does not appear as a bright point or a blazing disk. It appears as absence. The region where it resides looks strangely dim compared with the energy that should be present there, and this absence is the first sign that a supermassive black hole sits in the heart of the galaxy. A black hole is defined not by what it emits, but by what it prevents from escaping. In the modern description of gravity, mass and energy curve spacetime, and that curvature guides the paths of planets, stars and light. If enough mass is compressed into a small enough region, the curvature becomes so extreme that all paths in that region turn inward. Even a beam of light, which in empty space would travel in a straight line, finds every possible path bent back toward the center. The boundary beyond which no path leads back out is called the event horizon. Inside this horizon, any object that has crossed the threshold continues inward and does not return. Sagittarius A star is an example of a supermassive black hole, a black hole whose mass is measured in millions of suns rather than in single stars. The sample image that many people associate with it, a blurred orange ring surrounding a darker interior, does not show the black hole itself. It shows light from hot gas in orbit around the event horizon. Radio telescopes spread across Earth, working together as the Event Horizon Telescope, combine their signals to resolve this glowing ring around the central darkness. The dark region is often described as the shadow of the black hole, a zone where light that would otherwise travel toward the telescopes is captured instead. In the case of Sagittarius A star, that shadow spans a region on the order of several tens of millions of kilometers across, yet from Earth, it subtends an angle so small that only a planet-sized observatory can distinguish it from a point. The object that casts this shadow cannot be directly imaged in the ordinary sense. It has no solid surface that reflects light. It has no visible crust or atmosphere that can be photographed. Its presence is inferred from the gravitational control it exerts on its surroundings. For many years, the evidence for Sagittarius A star came from the orbits of nearby stars. Astronomers tracked these stars in infrared light, a band that can pierce some of the dust that obscures the galactic center. They saw stars moving along tight, fast orbits around a common unseen focus. In some cases, a single star completed a full circuit in a period measured in only a few decades. The speed of these stars and the size of their orbits revealed that several million solar masses must be confined within a volume smaller than the orbit of Neptune. No known cluster of ordinary stars, neutron stars, or other compact objects could be packed so densely without quickly collapsing. The simplest explanation that fits the data is a single supermassive black hole. The idea that such an object could exist arises naturally from the mathematics of general relativity. When Einstein introduced this theory of gravity in the early 20th century, he described how space-time geometry responds to mass and energy. Shortly afterward, Carl Schwarzschild found a solution to Einstein's equations representing a point mass. This solution contains an event horizon, and at its center a place where the curvature of space-time becomes formally infinite. That central point is called a singularity. Einstein himself was uneasy with this prediction. He suspected that the singularity might be an artifact of pushing the theory beyond its proper range, or that some aspect of real matter would prevent this extreme state from being reached. For decades, black holes remained a theoretical curiosity. Only in the second half of the 20th century did observational evidence begin to accumulate that such objects are not only real but common. Stellar explosions leave behind compact remnants that can feed on nearby gas. Binary star systems show signs that one member is a compact dark object accreting matter from its companion. In distant galaxies, extremely bright cores called quasars shine, with the energy released as gas spirals into central supermassive black holes. Sagittarius A star is part of this broader picture, but it holds a special role because it is the nearest supermassive black hole that can be studied in detail. In a sense, it serves as a laboratory for the physics of strong gravity. The orbits of nearby stars, the motion of gas clouds, and the pattern of radio emissions from the inner region all provide independent clues about the nature of the central object. Together, they form a consistent picture of a compact body whose properties match those predicted for a black hole. Yet as the evidence has grown stronger, the theoretical puzzles have grown deeper. If the core of Sagittarius A star contains a true singularity, then spacetime in that region ceases to behave in a way that current physics can describe. If the event horizon functions exactly as general relativity suggests, then any information carried by matter and radiation that cross it is permanently hidden from the outside universe. These implications challenge the idea that physical laws should be complete and consistent everywhere. The black hole at the center of the galaxy thus becomes more than an astronomical object. It becomes a test of the foundations of physics. The quiet radio source catalogued as Sagittarius A star, the drifting stars in its grip, and the smeared ring of light resolved by interferometers together define a single compact mystery. Everything known about its mass size and influence fits smoothly into the framework of general relativity, yet that same framework predicts an interior that cannot be reconciled with quantum mechanics. This tension between a successful description of the outer environment and a breakdown of theory at the center is what makes Sagittarius A star an ideal starting point for exploring the black hole paradox that still unsettles modern physics. A striking feature of black holes in general relativity is their apparent simplicity. Once a black hole settles down after its formation and stops ringing with transient disturbances, it can be fully described, at least in principle, by just three global properties. The first is mass, which sets the overall strength of its gravitational pull and the size of its event horizon. The second is spin, also called angular momentum, which tells how rapidly the black hole rotates and how strongly it drags spacetime around with it. The third is electric charge, a measure of any net imbalance between positive and negative charges that have fallen in. According to the standard solutions of Einstein's equations, these three quantities completely determine the exterior spacetime of a black hole. This statement is sometimes summarized by saying that black holes have no hair, meaning that all the detailed information about the matter that formed them, or later fell in, is erased from the outside description, leaving only these three coarse numbers. A stellar core made of iron, a cloud of hydrogen gas, or a stream of dark matter particles would after collapse produce the same exterior geometry if the mass, spin and charge are the same. From the viewpoint of an outside observer who only measures orbits' light paths and gravitational waves, there is no way to tell what specific material history led to the black hole now present. This radical simplification is part of what makes black holes such clean theoretical objects. They are not cluttered by the complex chemistry and thermodynamics found in stars and planets. Instead, they are pure solutions of a geometric theory of gravity. Yet the same simplicity carries a disturbing implication. If the external description forgets everything but mass, spin and charge, what happens to all the finer details that once distinguished one configuration of matter from another? In ordinary physics, information about a system can be scrambled and dispersed, but it is not supposed to be destroyed. In principle, given perfect knowledge of a system and its environment at one moment, the fundamental equations allow one to reconstruct its state at earlier times. In the case of black holes, the mapping from a wide variety of initial conditions to a small set of final parameters appears to violate this principle. Different initial states flow into the same final state, and there is no way within classical general relativity to recover what was lost. This tension is sharpened when thermodynamic ideas are applied to black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes behave as thermal objects. They have an entropy, a measure of the number of microscopic states consistent with their macroscopic parameters, and they have a temperature associated with a faint radiation predicted to emerge from quantum effects near the horizon. The entropy of a black hole is found to be proportional not to its volume but to the area of its event horizon. This is a remarkable and counterintuitive result. For ordinary matter, entropy usually scales with volume because more space allows more possible configurations of particles. For a black hole, the relevant measure appears to be the surface area, and the entropy carried by even a modest stellar mass black hole far exceeds that of the matter that likely formed it. The black hole thus seems to be a highly efficient information storage device, yet the external simplicity of its description raises the question of where that information actually resides and how it might be accessed in any meaningful way. These considerations return attention to the internal structure of the black hole, where the classical theory predicts a singularity. In the simplest non-rotating case, the singularity takes the form of a point in spacetime where curvature becomes infinite. In rotating black holes, the singularity can take on a ring-like structure. In all cases, however, the singular region is hidden behind the event horizon, and no signal from it can reach the outside. This makes it impossible within the classical theory to test the nature of the singularity by direct observation. Nonetheless, the presence of an infinite curvature is widely regarded as a sign that the theory is being pushed beyond its valid regime. It suggests that some new description, likely involving quantum aspects of gravity, must replace the classical one in the deep interior. But because that new description is not yet fully known, the fate of information inside a black hole remains ambiguous. The apparent simplicity of black holes from the outside thus masks a profound internal unknown. On one hand, astronomers can calculate precise predictions for orbits around a black hole, for the shape of its photon ring, and for the gravitational waves it emits when it merges with another. These predictions match observations with impressive accuracy. On the other hand, the same theory that provides this accuracy insists that somewhere inside, beyond the event horizon, lies a region where space-time ends in a singularity and where familiar rules no longer apply. This split personality gives black holes a special role in modern physics. They're both reliable test beds and clear signals that current theory is incomplete. The paradox is sharpened further when one considers the near absence of electric charge in astrophysical black holes. In practice, most black holes in the universe are expected to be electrically neutral to a very good approximation, because any significant charge would quickly be neutralized by attracting opposite charges from the surrounding plasma. This leaves mass and spin as the main parameters of interest. A given black hole can thus be described to a high degree of approximation by just two numbers. The reduction from 3 parameters to 2 only intensifies the original puzzle. The more economical the description, the more severe the loss of visible detail, and the more pressing the question of whether this loss represents a true physical erasure or only a limitation of the classical viewpoint. In this way, a seemingly simple mathematical statement about mass, spin, and charge leads directly to one of the deepest unsolved questions in theoretical physics. The black hole that appears so straightforward in the equations and so featureless in its external geometry conceals an interior story that existing frameworks cannot yet narrate. Black holes appear in nature across a wide range of masses, and this variety hints at a kind of cosmic family. At the small end of this family, at least in relative terms, are stellar mass black holes. These objects form when a massive star exhausts the nuclear fuel in its core. As long as nuclear reactions proceed, they produce an outward pressure that counters gravity. When the fuel runs low, that pressure drops, the core can no longer support its own weight, and it begins to collapse. If the collapsing core is sufficiently massive, no known force can halt the contraction, and the result is a black hole whose mass is typically several to a few dozen times that of the Sun. The outer layers of the star are blown away in a supernova explosion while the core continues inward. The event horizon that forms around this core spans a region only a few tens of kilometers across, yet its gravity can control the motion of matter over much larger distances. For many years, evidence for stellar mass black holes came mainly from X-ray observations of binary systems. In such systems, an ordinary star orbits an unseen companion. Gas is drawn from the visible star toward the compact object, forming a disk that spirals inward. As this gas falls deeper into the gravitational potential, it heats to high temperatures and emits X-rays. In some systems, the pattern of X-ray variability and the dynamics of the orbiting star strongly indicate that the compact companion is too massive and too small to be a neutron star. The simplest interpretation is that it is a stellar mass black hole. More recently, detectors that measure gravitational waves have added a new window on this population. When two stellar mass black holes orbit each other in a close binary, they radiate gravitational waves and slowly spiral together. In the final moments of their inspiral and merger, they emit a burst of gravitational radiation with a distinctive waveform. These signals have been recorded many times. The inferred masses and spins of the merging objects match expectations for stellar mass black holes, and show that such systems are common. Moving up in mass theory predicts the existence of intermediate mass black holes. These would bridge the gap between the stellar mass range and the supermassive range, with masses perhaps between a few hundred and a few 100,000 suns. For a long time, evidence for such intermediates remained sparse and ambiguous. Some unusually bright X-ray sources in nearby galaxies seem to require compact objects more massive than ordinary stellar remnants, yet not as extreme as the central engines of quasars. In dense star clusters, dynamical studies suggested that an unseen mass larger than a typical star but smaller than a galactic nucleus might sit at the center. Gravitational wave detections have also hinted at merging objects whose masses lie above the usual stellar range. Taken together, these clues support the idea that intermediate mass black holes exist, but they are far from catalogued in a systematic way. They remain in many respects the missing members of the family. At the top of the mass scale are the supermassive black holes. These giants contain millions to billions of solar masses confined within regions smaller than the orbits of planets. They sit at the centers of large galaxies where their gravity influences the motion of nearby stars and gas. The brightest examples reveal themselves as quasars' extraordinarily luminous galactic nuclei, visible across vast cosmic distances. Quasars radiate as matter accretes onto their central black holes. As gas falls inward through an accretion disk, friction and magnetic turbulence convert gravitational energy into heat and radiation. The efficiency of this process can exceed that of nuclear fusion in stars. Consequently, even a modest inflow of matter can power a quasar that outshines its entire host galaxy. The existence of supermassive black holes at the present epoch is no longer in serious doubt. Observations of stellar motions in the centers of nearby galaxies, including the Milky Way, provide strong dynamical evidence for compact central masses with properties consistent with black holes. Very long baseline interferometry, which links widely separated radio telescopes, has imaged the regions near the event horizons of a few nearby supermassive black holes, revealing the anticipated photon ring and central shadow. These measurements agree with general relativistic predictions for objects characterized mainly by mass and spin. Yet the story becomes more puzzling when one looks back in time. Light from very distant quasars has been travelling for the majority of the age of the universe before reaching Earth. This means that telescopes, by observing such quasars, are effectively looking into the past. Some of the brightest known quasars appear at epochs when the universe is only a few 100 million years old. At that time, the first generations of stars and galaxies are only beginning to form, yet the black holes at the centres of these early quasars already contain masses of hundreds of millions or even billions of suns. Growing a black hole from a stellar mass seed to such a large mass requires sustained accretion or repeated mergers. In simple models, there is a characteristic rate at which matter can fall into a black hole, while the outward pressure of the radiation produced by accretion balances the inward pull of gravity. This rate sets a natural timescale for growth. If a black hole accretes steadily at this limiting rate, its mass increases exponentially with time doubling at roughly fixed intervals. When this growth pattern is applied to a stellar mass seed, the time available between the birth of the first stars and the appearance of the earliest observed quasars seems barely sufficient, and in many scenarios it appears inadequate. The timeline is tight, and any interruptions in accretion make the problem more severe. This mismatch encourages astrophysicists to consider alternative formation paths. One possibility is that the seeds of supermassive black holes are not ordinary stellar remnants, but instead formed by direct collapse of massive gas clouds. In this picture, a dense metal-poor cloud in the early universe loses its ability to fragment into individual stars and instead collapses as a whole into a single object that may quickly form a black hole with a mass much larger than that of a typical star. Such a direct collapse black hole would start the growth process already in an intermediate mass regime, easing the timing constraints. Another scenario involves dense star clusters in which repeated collisions and mergers build up a very massive star that then collapses into a large black hole. In both cases, intermediate mass black holes play a central role as stepping stones toward the supermassive range. They serve as the link between stellar remnants and the engines of quasars. However, the observational evidence for large numbers of intermediates remains incomplete. The cosmic family portrait thus looks uneven. The smallest and largest members are visible in many ways, but the middle range is relatively faint and hard to detect. This incomplete census is not just a cataloguing issue. It matters for understanding how galaxies and their central black holes grow together. Observations indicate a correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. This suggests some form of coevolution, where the growth of the galaxy and of its black hole are linked. Feedback from accretion in the form of radiation and jets can heat and expel gas from the surrounding region, influencing future star formation. At the same time, inflowing gas that feeds the black hole also fuels starbirth. The details of these interactions depend on when and how the central black hole acquires its mass. If supermassive black holes assemble through many mergers of smaller black holes, then gravitational wave signals from the early universe should carry traces of this history. If they instead arise quickly from direct collapse, then certain kinds of bright transient events may accompany their birth. Current observations are not yet sufficient to discriminate decisively between these possibilities. As a result, the cosmic black hole family remains an open story. Stellar mass members are comparatively well understood. Supermassive ones are well attested but puzzling in their early growth, and intermediate mass members are inferred but elusive. This imbalance between what is detected and what is required by simple formation models is a clear example of how data can point beyond current theory. The basic framework of gravitational collapse and accretion explains much, yet the presence of fully grown supermassive black holes in a very young universe places strain on straightforward scenarios. This tension encourages further observation and more detailed modelling, and it prepares the ground for more speculative ideas in which new kinds of black holes formed under extreme early conditions might help to fill the gaps. The known black hole family already stretches across many orders of magnitude in mass, from stellar remnants a few times heavier than the Sun to giants with billions of solar masses. Yet some theories of the early universe suggest there could be another branch of this family composed of much smaller black holes that formed not from dying stars but directly from the conditions that prevailed shortly after the Big Bang. These hypothetical objects are called primordial black holes. They would arise during the first fractions of a second when the universe was extremely hot, dense, and rapidly expanding. In that early era, matter and radiation were not perfectly smooth. Tiny fluctuations in density seeded by quantum effects and later stretched by cosmic expansion created regions that were slightly more crowded than average. In the standard picture, these slight overdensities eventually grew into galaxies and clusters of galaxies under the pull of gravity. In some variants of the picture, however, certain regions could have become so dense that they crossed a critical threshold and collapsed directly into black holes. Unlike stellar mass black holes, which have a fairly narrow mass range determined by the physics of massive stars, primordial black holes could have formed across a broad spectrum of masses. Some might have been as light as mountains, others as heavy as stars, and still others in intermediate regimes. The exact mass distribution would depend on details of the early universe that are not yet fully known, such as the shape of the primordial power spectrum of fluctuations, or the behavior of fields that drove inflation. This sensitivity turns primordial black holes into potential probes of high-energy physics, but it also introduces considerable uncertainty. What makes them particularly intriguing is that they do not require any new type of particle or force. They are composed entirely of ordinary gravity acting on ordinary matter and radiation. For this reason, they have been proposed as candidates for dark matter, the unseen component that seems to outweigh visible matter by a large factor and that shapes the rotation curves of galaxies and the dynamics of galaxy clusters. If a significant fraction of dark matter were made of primordial black holes, then the missing mass problem could be addressed without invoking new elementary particles beyond those already known. Instead of a diffuse invisible fluid, the dark matter would be a population of compact objects scattered throughout galactic halos, passing silently through the outskirts of galaxies, including the Milky Way. Testing this idea requires careful consideration of how such black holes would reveal themselves. One avenue is gravitational lensing. A compact mass passing in front of a distant star can act as a lens temporarily magnifying the star's light. Surveys have monitored millions of stars to search for such microlensing events. The rate and characteristic timescales of these events constrain how many compact objects of a given mass can exist in galactic halos. For certain mass ranges, the lack of observed lensing events rules out primordial black holes as the dominant form of dark matter. In other ranges, the constraints are weaker, leaving open windows where primordial black holes could still contribute significantly. Other approaches involve the cosmic microwave background, the afterglow of the Big Bang. Primordial black holes accreting gas in the early universe would release energy which could alter the ionization history of the cosmic plasma and leave an imprint on the pattern of temperature fluctuations seen in this background radiation. Observations of the microwave sky therefore limit the abundance of such objects. Additional constraints come from the dynamics of wide binary stars, from the stability of star clusters, and from the absence of strong gamma-ray signals that would be expected if many small black holes were evaporating today. These diverse lines of evidence have excluded some regions of parameter space, but others remain uncertain. The subject is active with different analyses, sometimes reaching slightly different conclusions depending on the assumptions they adopt. A key ingredient in these discussions is Hawking radiation. When quantum field theory is applied to curved spacetime near the horizon of a black hole, it predicts that black holes are not completely black. Instead, they emit a very faint radiation, with a thermal spectrum as if they had a temperature. This Hawking temperature is inversely proportional to the mass of the black hole. Large black holes, such as those in galactic centers, have extremely low temperatures and radiate negligibly. They gain mass from ambient gas and radiation much faster than they lose it through Hawking radiation. Small black holes, by contrast, have higher temperatures and radiate more strongly. As they emit this radiation, they lose mass, which causes their temperature to rise, further accelerating the process. In this way, a sufficiently small black hole can slowly evaporate over time. For black holes with masses comparable to those of stars or larger, the evaporation timescale far exceeds the age of the universe, so Hawking radiation has minimal practical effect. For primordial black holes that formed with much smaller masses, however, evaporation could be significant. A primordial black hole with an initial mass below a certain threshold would have evaporated completely by the present epoch. One with mass near that threshold would be in its final stages of evaporation today, releasing a burst of high-energy photons, particularly gamma rays. Astronomers therefore search for signs of such bursts. A diffuse background of gamma rays or transient events with specific spectral shapes could hint at the last moments of ancient primordial black holes. The absence of a clear signal places further limits on how many such objects could exist in certain mass ranges. Yet here again the situation is subtle. Astrophysical processes unrelated to black holes also produce gamma rays. Separating a potential primordial black hole signature from other background sources is challenging, and assumptions about the distribution of black holes and their environments affect the predictions. As a result, while the most extreme possibilities can be ruled out, there remains some room for primordial black holes to contribute to dark matter, in particular mass windows. This complex pattern of partial exclusions and remaining gaps sustains interest in the idea. Even if primordial black holes make up only a fraction of the dark matter, their existence would reveal new information about the conditions of the early universe. Their formation would require density peaks above a threshold value, which in turn reflects the behavior of fields and fluctuations at energies far beyond those accessible in laboratories. In this way, an apparently astrophysical question about dark compact objects becomes tied to the physics of inflation phase transitions in the early universe and the possible presence of additional fields or symmetry-breaking events. The search for primordial black holes thus proceeds on multiple fronts. Astronomers refine microlensing surveys, gamma-ray observations, and gravitational wave analyses. Theoretical work explores how different early universe scenarios would shape the mass spectrum of primordial black holes, and how those spectra would manifest in present-day data. So far, no unambiguous detection has been made. No definitive signature points to a population of black holes that formed before the first stars. Yet the constraints are not complete, and in some mass ranges the possibility remains open. This mixture of strong bounds and persistent openings is characteristic of frontier problems in astrophysics. Data slices away large swathes of parameter space, but the surviving regions are enough to keep speculative ideas viable. Primordial black holes occupy such a region. They are simple in their basic definition, rely only on known gravitational physics, and offer an appealing link between black holes' dark matter and the early universe. At the same time, they are elusive, difficult to detect directly, and easily confused with other phenomena. Their potential presence or absence carries implications that reach far beyond black hole astrophysics. If they exist in the right numbers and masses, they may help explain the origin of supermassive black holes, contribute to dark matter, and provide a fossil record of conditions in the first instance after the Big Bang. If they do not, then the universe has chosen a different path, and other explanations must be found for the missing mass and the early growth of quasars. In either case, the notion that tiny black holes may have formed in the primordial fireball lived for billions of years, and in some cases quietly evaporated by now illustrates how the concept of a black hole can extend from the cause of galaxies down to scales where quantum effects dominate. It also shows how the same framework that describes the massive engine at the centre of the Milky Way naturally raises the possibility of much smaller long-vanished shadows that may still leave subtle traces in the radiation and structure of the universe today. In general relativity, gravity is no longer a force acting within a fixed stage, but a feature of the stage itself. Mass and energy tell space-time how to curve, and that curvature tells matter and light how to move. In gentle situations, such as the orbit of Earth around the Sun, this curvature can be described as a smooth, almost imperceptible bending of trajectories compared with straight lines in empty space. The mathematics of Einstein's equations captures this behavior in a compact set of relations between geometry and energy. For many configurations of matter, the resulting space-time is well behaved everywhere. The curvature may be strong in some regions and weak in others, but it remains finite and the equations can be applied consistently at every point. Black holes stand out as cases where this reassuring picture breaks down. The simplest route to this breakdown begins with the solution found by Carl Schwarzschild shortly after Einstein presented his theory. Schwarzschild considered the space-time outside a spherical mass that is not rotating and not changing with time. The result is a specific metric, a mathematical description of distances and times in that region. Far from the mass, this space-time looks almost flat. Closer in, the curvature increases and the paths of freely falling particles deviate more strongly from straight lines. At a certain radius, however, the form of the metric suggests that something special happens. In the original coordinates, some components of the metric appear to diverge. At first glance, this looks like a singularity, but it is a singularity of description, not of geometry. By changing coordinates, one can show that this radius corresponds to a perfectly regular surface in space-time now recognized as the event horizon. It is a boundary from which no light or material object can return to the exterior region. Inside this horizon, the roles of space and time change in a way that forces all future directed paths to move inward toward the center. Deeper in, at the central point, the situation is different. No change of coordinates can remove the divergence. Curvature invariants built from the metric and its derivatives grow without bound. This is a genuine singularity, a place where the classical description ceases to make sense. An object falling toward this central region experiences tidal forces that increase without limit as it approaches. The timescale over which these forces change grows shorter, and physical quantities that are otherwise finite become undefined. In technical terms, the space-time is geodesically incomplete, meaning that certain paths simply end after a finite interval, with no way to extend them further within the theory. The emergence of such singularities is not restricted to the simple Schwarzschild case. Theorems developed in the 1960s by Roger Penrose and Stephen Hawking demonstrate that under broad and reasonable conditions, gravitational collapse of sufficiently dense matter inevitably leads to singularities in general relativity. These results do not depend on special symmetries or particular matter distributions. They indicate that once certain thresholds of density and curvature are crossed, the theory predicts its own breakdown. In most known solutions, these singularities are hidden behind horizons. This expectation is formalized in the cosmic censorship hypothesis, which in rough terms suggests that the universe does not permit naked singularities visible from afar. If this hypothesis holds, then every singularity created in realistic collapse is safely contained behind an event horizon. The external observer never sees the singular region itself, only its indirect influence through the overall gravitational field. In that sense, the theory protects its own breakdown from observational scrutiny. The singularity remains a problem in principle, a sign that the description is incomplete, but it does not obviously contaminate predictions for observable quantities outside the horizon. This separation between interior pathology and exterior predictability is part of what allows physicists to use black hole solutions as practical tools. For many astrophysical purposes, it is enough to know that a compact object behaves externally like a black hole of a given mass and spin. The precise structure of the interior is irrelevant for calculating orbital dynamics, accretion flows, or gravitational wave emission from mergers. Yet from the standpoint of fundamental physics, ignoring the singularity is not satisfying. The existence of a region where spacetime curvature becomes infinite, and where the usual laws of conservation and causality may fail, raises questions about the completeness and consistency of the theory as a whole. In many physical theories, singularities signal the need for a more refined description. For example, the classical picture of an electron as a point charge leads to infinities that are resolved in quantum electrodynamics by treating fields and particles in a new framework. By analogy, many physicists expect that a full theory of quantum gravity will smooth out or otherwise replace the classical singularity. In such a theory, spacetime may have a discrete or fluctuating structure at extremely small scales, or familiar concepts of space and time may emerge from more basic entities. Whatever the detailed form, the hope is that curvature and energy densities remain finite, and paths do not simply terminate in unphysical endpoints. The difficulty lies in the fact that no complete and experimentally confirmed quantum theory of gravity exists yet. Several candidate frameworks, such as string theory or loop, inspired approaches suggest ways in which singularities might be resolved. Some replace the central point with an extended structure. Others introduce new phases of spacetime in which effective repulsive effects counteract collapse at very high densities. In some models, the interior of what appears externally as a black hole might connect to another region, perhaps in a distant part of the same universe, or even in a separate branch of spacetime. In others, the collapse might bounce turning contraction into expansion, and creating a new domain on the other side of the would be singularity. These possibilities remain speculative, constrained more by mathematical consistency than by direct data. Nonetheless, they show that the notion of a singularity as a simple point of infinite density may not survive in a quantum description. The presence of an event horizon complicates attempts to test such ideas. Since nothing from inside can escape any modification of the deep interior must imprint itself indirectly through subtle effects near the horizon or in the global evolution of the spacetime. One approach is to study how small perturbations behave around black holes and to compare the resulting gravitational wave signatures or photon ring structures with those predicted by classical general relativity. If observed signals deviate in specific ways, they could hint at new physics. So far, however, measurements have been consistent within uncertainties with the classical model. This agreement strengthens confidence in general relativity in the strong field regime, but does not rule out modifications confined to regions very close to or inside the horizon. The notion that space-time itself can tear in the sense of becoming singular thus remains at the edge of current knowledge. It is both a robust prediction of classical general relativity and a likely indicator of that theory's limits. It shows that gravity, when pushed to extremes, creates situations where the usual understanding of cause and effect, conservation and smooth evolution fails. Black holes are the naturally occurring laboratories where this failure is expected to occur. The paradox is that these laboratories are by design shielded from direct inspection. The region where theory breaks is the region from which no signal returns. This tension motivates the search for frameworks in which the horizon is not a perfect separator, or in which the singularity is replaced by a more benign core. It also underlies the concern that whatever happens in the interior, may affect how information is treated, bringing general relativity into conflict with quantum mechanics. The singularity problem is therefore not an isolated mathematical curiosity. It is the first sign that black holes force a confrontation between otherwise successful theories, and that spacetime, when crushed by gravity beyond a critical point, demands a new description that has yet to be fully worked out. The singularity problem already indicates that classical general relativity cannot be the final story for black holes, but the tension with quantum mechanics becomes most acute when information is considered. In ordinary quantum theory, the evolution of an isolated system is reversible at the fundamental level. If the exact state of a system at one moment is known, the equations of motion allow in principle reconstruction of its state at earlier times. This feature is often summarized by saying that information is conserved. The probabilities of outcomes may change with time, and a system may appear to lose coherence when it interacts with an environment, but the underlying microscopic description remains unitary and complete. Black holes seem to threaten this principle. The simplest thought experiment begins with matter in a well-defined quantum state, collapsing under its own gravity. A massive star, for example, forms with a particular composition, internal structure and pattern of quantum correlations among its constituent particles. If the star is sufficiently massive, its core eventually collapses to form a black hole. In classical general relativity, everything about the collapsing matter except its total mass, angular momentum and electric charge becomes inaccessible to the exterior. The event horizon forms, and whatever details once existed inside the star pass behind this horizon. From that point on, the external description is given by a black hole solution characterized only by a few parameters. At first, this looks like a simple case of coarse graining. Many different initial configurations lead to the same macroscopic final state, but one might still imagine that the detailed information is somehow preserved in the interior, inaccessible but not destroyed. In the 1970s, Stephen Hawking added a crucial new ingredient. By combining quantum field theory with the curved spacetime around a black hole, he showed that black holes are not completely dark. Quantum fluctuations near the horizon cause the emission of radiation that appears thermal when measured far away. This Hawking radiation carries energy away from the black hole, causing it to lose mass over time. For black holes with stellar or larger masses, the temperature of this radiation is extremely low, and the rate of mass loss is negligible, compared with accretion from the environment. For hypothetical small black holes, especially primordial ones, the effect can be significant, leading to slow evaporation over cosmic timescales. The key point is that Hawking's original calculation indicates that the emitted radiation is almost perfectly thermal. Its spectrum depends only on the mass, spin and charge of the black hole, not on the detailed state of the matter that fell in. If a black hole forms from matter in a pure quantum state and then evaporates completely into thermal radiation, the final state is mixed and appears to carry much less information than the initial one. The mapping from the initial to the final state is not reversible in the usual quantum mechanical sense. Information seems to disappear from the observable universe, not just become scrambled. This is the black hole information paradox. It is not merely a technical issue, but a direct clash between two pillars of modern physics. On one side stands general relativity with its prediction of an event horizon that separates interior from exterior regions, and its semi-classical extension that produces thermal Hawking radiation. On the other side stands quantum theory, with its insistence on unitary evolution and information conservation. If the black hole truly evaporates away as the Hawking process suggests, and if the radiation is exactly thermal, then something must give. Either information is lost or quantum evolution is modified, or the semi-classical analysis breaks down in a subtle way that allows the outgoing radiation to encode more information than the initial calculation reveals. Much effort has gone into examining each of these possibilities. The option that information is simply destroyed in black hole evaporation would require a change in the foundations of quantum mechanics. Time evolution would no longer be strictly unitary. Some have argued that such a modification might be acceptable if it is confined to extreme gravitational environments and if its observable effects elsewhere are negligible. However, this route raises concerns about energy conservation and about the consistency of quantum theory more broadly. Small violations in one context can in principle propagate into others. As a result, most researchers prefer to preserve unitarity and to seek resolutions that keep quantum mechanics intact. Another class of ideas explores whether information might remain stored in a remnant. In this scenario, a black hole evaporates down to a very small yet stable object that retains all the information about what formed it, even though its mass has shrunk. The remnant would have to possess an enormous internal capacity for distinct states while having tiny mass and size. This seems to conflict with expectations from quantum field theory, which disfavors such highly degenerate low-mass objects. Remnants also pose challenges for cosmology, because large numbers of them might be created and could affect the balance of matter and energy in the universe. These difficulties do not exclude remnants outright, but they make them a less favoured solution. The remaining broad possibility is that the semi-classical calculation of Hawking radiation is incomplete. In Hawking's original work, the radiation emerges from quantum fields propagating in a fixed curved background. The black hole geometry is treated classically, and the back reaction of the radiation on the spacetime is included only in an average way through the gradual loss of mass. It is reasonable to suspect that a more comprehensive treatment of quantum gravity would modify the result. In many proposals, the outgoing radiation is still approximately thermal in its local properties, but carries subtle correlations that encode the information about the infalling matter. From this viewpoint, the paradox arises because the leading order calculation ignores these correlations and treats the radiation as exactly thermal and independent. Over very long timescales, these correlations could gradually reveal the information restoring unitarity. A useful way to frame this is through the concept of the Page curve named after Don Page. In a unitary scenario, the entropy of the radiation emitted by an evaporating black hole should initially increase as more quanta are emitted, but eventually reach a maximum and then decrease as the late radiation becomes more strongly correlated with the early radiation. The total entropy of the combined system would remain constant. In Hawking's original calculation, by contrast, the entropy of the radiation grows steadily until the black hole disappears and no downturn occurs. Computing the Page curve in a full theory of quantum gravity has proved difficult, but recent progress using techniques inspired by holographic duality and quantum extremal surfaces has produced results consistent with unitary evolution in certain simplified models. In these approaches, the entropy of the radiation follows a Page-like curve, suggesting that quantum gravity effects can in principle reconcile black hole evaporation with information conservation. Nonetheless, it is not yet clear how these insights extend to realistic black holes in asymptotically flat spacetime or to regimes far from the idealized setups where calculations are tractable. A different line of thought focuses on the structure of the event horizon itself. If the horizon is not a completely smooth, featureless surface at the quantum level, then infalling and outgoing degrees of freedom might interact in ways that allow information to be transferred to the radiation. Proposals along these lines include ideas of soft hair, subtle field configurations on the horizon that store information, and more radical suggestions such as firewalls in which the region just outside the horizon becomes highly excited and breaks the usual expectation that an infalling observer experiences nothing special at the horizon. These scenarios attempt to preserve unitarity by modifying the behavior of fields near the horizon, but they often conflict with other principles such as the equivalence principle, which states that locally in free fall, The laws of physics should resemble those in unaccelerated frames. The interplay among these constraints forms part of the so-called firewall debate. Behind the technical details lies a simple tension. Classical general relativity presents the horizon as an ordinary region of space-time where curvature is finite and freely falling. Observers pass through without encountering infinite forces. Quantum field theory in curved space-time, when applied in that setting, predicts thermal radiation, but no violent effects at the horizon for large black holes. Demanding strict unitarity, however, seems to require either long-range correlations that somehow circumvent the locality built into the classical picture, or drastic changes in the near-horizon structure. Each option challenges some aspect of the usual assumptions. The information paradox therefore stands as a precise formulation of the broader conflict between gravity and quantum mechanics. It is not just that singularities indicate a breakdown of classical theory in extreme regimes. Even before reaching the singularity, the combination of horizons, quantum fields, and evaporation leads to conclusions that cannot be reconciled with all existing principles at once. Something in the standard set of assumptions must give way. The question is, which part? Current observations do not yet distinguish among the proposed resolutions. Hawking radiation from astrophysical black holes is far too weak to measure directly, and any deviations from classical behavior near horizons are extremely subtle for large masses. Gravitational wave signals from mergers and images of photon rings around supermassive black holes so far match the predictions of classical general relativity with no clear anomalies. This absence of evidence does not resolve the paradox. Instead, it suggests that whatever new physics operates to reconcile information, conservation with black hole evaporation, must do so in a way that preserves the successful large-scale predictions of general relativity while altering its behavior in regimes that are currently beyond direct experimental reach. In this sense, the information paradox is less a sign of failure and more a guide. It indicates that the path to a consistent theory of quantum gravity runs through the detailed structure of black holes, their horizons, and their radiation. It also encourages exploration of alternative models of black holes, in which classical singularities and strict horizons are replaced by new structures that can store and release information without violating known principles. These models form the subject of several proposals that aim to regularize black holes and to remove the singularity while preserving as much as possible their observed external appearance. In seeking to resolve the singularity and information problems without discarding either general relativity or quantum mechanics, some theorists turn to string theory, a proposed framework in which the basic building blocks of nature are not point particles, but extended objects. In this view, every familiar particle, such as an electron or a quark, corresponds to a particular vibrational mode of a tiny string. There are also higher dimensional extended objects, often called branes, that can carry charges and support fields. When gravity is included in this framework, a certain vibrational mode behaves like the graviton, the quantum of the gravitational field. This built-in presence of gravity makes string theory a candidate for a unified description of all forces, including those relevant in the interior of black holes. Within this setting, a particular proposal known as the fuzzball picture attempts to replace the classical notion of a black hole with singularity and empty interior by a different kind of object. In the fuzzball view, what appears macroscopically as a black hole is at the microscopic level a complicated configuration of strings and branes. Instead of matter collapsing to a point of infinite density, hidden behind a smooth event horizon, the degrees of freedom that carry the mass and charge of the object spread out over a region of finite size. The interior is filled with structure down to the scale where quantum gravity effects become important. The name fuzzball reflects the idea that the sharp boundary and empty interior of the classical solution are replaced by an extended intricate arrangement of fundamental ingredients. different ways of arranging strings and branes with the same total mass spin and charge correspond to different microstates of the black hole, the black. From far away, these microstates all look nearly the same. The gravitational field they produce matches the classical black hole metric to a good approximation. Up close, however, the detailed structure can differ. In some explicit constructions, there is no horizon in the traditional sense and no singularity. Instead, space ends in a smooth but highly curved region, where the density of string and brane degrees of freedom becomes large. One of the motivations for the fuzzball picture is that it provides a way to count microstates that reproduces the expected entropy of certain black holes. In particular regimes where string theory is best understood, such as supersymmetric configurations in higher dimensional spacetimes, the number of distinct bound states of strings and branes with a given set of charges can be calculated. The logarithm of this number, when compared with the area of the corresponding classical horizon, matches the Bekenstein-Hawking entropy formula. This agreement suggests that the microstates of a black hole in string theory are indeed realized as specific fuzzball-like configurations. If this viewpoint is taken seriously, it offers a natural route to resolving the information paradox. Each fuzzball microstate is a pure quantum state, with a definite configuration of strings and branes. Radiation emitted from such an object need not be exactly thermal. It can carry detailed information about the particular microstate, encoded in subtle correlations among the outgoing quanta. When averaged over many microstates, the radiation may appear approximately thermal, but for a specific microstate the evolution is unitary and information is conserved. Infalling matter does not disappear behind a featureless horizon. Instead, it interacts with the string and brane structure near the would-be horizon, and its information is scrambled and re-emitted over time in the radiation. In this way, the fuzzball picture replaces the classical event horizon with a quantum surface that can absorb and re-emit information without invoking a singularity. The apparent simplicity of the black hole exterior, characterized only by mass and spin, is then understood as an emergent property. It reflects the fact that many different microstates produce very similar gravitational fields at large distances. The richness of the underlying structure is hidden on scales comparable to the horizon radius, where current observations have limited resolution. From an observational standpoint, a fuzzball would be almost indistinguishable from a classical black hole in many respects. The orbits of stars and gas in its vicinity, the shape of its photon ring, and the gravitational waves emitted in mergers would in the leading approximation match those predicted by general relativity. Only very subtle deviations, perhaps in the late-time tail of ring-down signals, or in correlations of emitted radiation, would betray the presence of a non-classical surface instead of an empty horizon. Detecting such deviations is beyond present capabilities. As a result, the fuzzball idea remains a theoretical proposal rather than an empirically confirmed description. Nonetheless, it has important conceptual consequences. By providing explicit examples in which the singular interior of a black hole solution is replaced by a regular configuration of fundamental objects, and in which the entropy can be understood in terms of counted microstates, it strengthens the case that black hole thermodynamics and information conservation can be reconciled within a quantum gravity framework. It also suggests that the classical picture of a black hole as a region of spacetime with a smooth horizon and an empty interior may be only an effective description that emerges when many microstates are averaged over. In this sense, the fuzzball program treats the black hole not as a fundamental entity, but as a coarse-grained label for a large ensemble of underlying configurations. There are, however, important limitations and open questions. Most explicit fuzzball constructions apply to highly symmetric extremal or near-extremal black holes in more than 4 spacetime dimensions, often with supersymmetry that simplifies calculations. extending these results to realistic astrophysical black holes, which are non-extremal, do not preserve supersymmetry, and exist in 4 large spacetime dimensions is challenging. It is not yet known whether every such black hole admits a complete description in terms of fuzzball microstates, or whether the fuzzball idea captures only a subset of possible configurations. Furthermore, even if the microscopic picture is correct, understanding the dynamics of formation and evaporation for a fuzzball in a realistic collapse remains an open task. It is one thing to count microstates in a carefully prepared setting, and another to show how the gravitational collapse of ordinary matter in a universe like ours selects and populates those states. The answers to these questions bear directly on the black hole paradox. If fuzzball-like objects are the generic endpoints of collapse in quantum gravity, then the singularity is eliminated and horizons are replaced by quantum surfaces where information is stored and eventually released. If instead fuzzballs are special cases that do not represent the full space of possibilities, then additional ingredients may be needed. Either way, the fuzzball program illustrates how a theory that treats space-time and matter in terms of extended fundamental objects can reshape the notion of a black hole. It turns what was once an idealized region of curved geometry into a many-bodied system with internal structure much as ordinary matter arises from atoms and molecules rather than from continuous media. In doing so, it keeps the external successes of general relativity while pointing toward a richer interior story in which information does not vanish but is hidden in the detailed arrangement of quantum building blocks. Beyond string-inspired pictures such as fuzzballs, another line of exploration aims to modify the interior of black holes while leaving their external appearance almost unchanged. In these proposals, the classical singularity is replaced not by a dense tangle of strings and brains, but by a new phase of space-time itself. One influential example is the idea of the gravitational vacuum star, often shortened in informal discussion to gravastar. In this model, what looks from the outside like a black hole is in fact a compact object made of 2 distinct regions separated by a thin shell. The innermost region is filled not with collapsing matter, but with a form of vacuum energy that has negative pressure. Such an energy density is similar in character to the one invoked to explain the accelerated expansion of the universe and is sometimes associated with the concept of dark energy. The outer region just beyond a certain radius resembles ordinary space-time with low curvature. Between them lies a shell of extremely dense matter that maintains the balance between the inward pull of gravity and the outward push of the vacuum energy. The structure can be arranged so that from far away, the gravitational field matches very closely that of a traditional black hole with the same mass. Light and matter orbiting at large distances follow trajectories that are almost indistinguishable from those in the classical solution. In this sense, a gravastar is a kind of black hole imposter. It has no singularity at the centre and no true event horizon. Yet for many observational purposes it behaves like a black hole. The motivation for such models is twofold. First, they remove the singularity by postulating that at very high densities and curvatures, space-time undergoes a phase change. Instead of continuing to collapse toward infinite curvature, the interior transitions into a state dominated by vacuum energy. This produces a repulsive gravitational effect that halts further collapse, much as the cosmological constant drives the large-scale expansion of the universe. Second, they provide a possible way to store information without letting it disappear behind an impassable horizon. In a gravastar, signals that reach the shell encounter an exotic medium rather than passing into a region from which no escape is possible. Depending on the detailed dynamics of the shell and core information, might be reflected, absorbed, or slowly re-emitted, but it is not forced into a classical singularity. Extending this idea, some theorists consider more elaborate structures in which the interior is not a single, uniform vacuum phase, but a layered arrangement of different regions. In one variant, there may be a compact core filled with vacuum energy, surrounded by a shell that itself contains trapped radiation or ultra-dense matter, and then an outer atmosphere wherein falling material accumulates. These nested configurations have been evocatively compared to sets of concentric spheres. In even more speculative proposals, one such object might be contained within another, forming a hierarchy reminiscent of nested dolls. Each layer modifies the local spacetime geometry, and the combined structure mimics the gravitational field of a black hole to high accuracy at distances accessible to observation. These shell-based models share a common feature with fuzzball ideas. They regularize the central region and avoid a point of infinite curvature. They also offer additional degrees of freedom in the form of shell dynamics or internal phases that could, in principle, encode information about the matter that formed the object. However, they differ in their underlying physics. Gravastars rely on macroscopic properties of space-time and vacuum energy, treating them as effective fluids with unusual pressure and density. They do not require a specific microscopic theory of strings or brains, though such a theory might ultimately underpin the exotic equation of state needed for the interior. As with fuzzballs, a major question is whether gravastars or similar objects could realistically form in astrophysical settings. The collapse of an ordinary massive star proceeds according to known nuclear and gravitational physics. For a gravastar to arise, the collapsing matter would need to undergo a transition into the vacuum-dominated phase before passing within its own Schwarzschild radius. The thin shell that separates interior and exterior would have to form with just the right tension and composition to maintain equilibrium. Whether such a sequence of events is dynamically plausible remains uncertain. Detailed simulations of collapse with exotic equations of state are challenging, and the relevant microphysics is not yet established. From an observational standpoint, distinguishing a gravastar from a traditional black hole is also difficult. Many proposed signatures rely on the absence of a true event horizon. For example, if matter falling toward the object accumulates on a surface, rather than crossing a horizon, it might eventually radiate away its energy in a delayed burst producing echoes in gravitational waves or in electromagnetic signals. In some models, the ring-down phase that follows a merger would show small deviations from the classical pattern caused by reflections from the inner shell. These deviations are expected to be subtle and can be masked by noise and by uncertainties in the modelling of the environment. Current observations of gravitational waves and black hole images are not yet precise enough to rule out all such alternatives. As instruments improve, they may begin to probe the parameter space of horizon-scale structures more tightly. Another family of proposals uses the language of regular black holes. These are solutions to modified gravitational field equations in which the central singularity is replaced by a finite core with maximum density. In some cases, the core again resembles a region dominated by vacuum energy. The geometric description of these objects is constructed so that the curvature remains finite everywhere, while the external field closely matches that of a classical black hole. These regular black hole metrics are often treated as effective models, capturing what might emerge from a full quantum gravity theory without specifying the microscopic details. The associated objects like gravastars would be observationally similar to black holes in many regimes, but differ in their treatment of the interior. Taken together, gravastars, regular black holes, and nested shell models illustrate one way in which theorists attempt to answer the paradoxes raised by classical collapse. Instead of allowing space-time to end in a singularity, they introduce new phases and structures that absorb and redistribute the extreme curvature. Instead of an absolute event horizon, they provide semi-permeable boundaries or surfaces that can interact within falling matter and radiation. These changes are designed to preserve the successful predictions of general relativity in the weak and moderate field regimes, while altering its behavior just enough in the deepest interior to avoid infinities and information loss. Yet these models also raise fresh questions. If the interior of A would-be black hole is filled with vacuum energy, what determines the value of that energy density? How does it relate to the dark energy that seems to drive cosmic acceleration on the larger scales? If shells of ultra-dense matter routinely form in collapse, why have no clear observational signs of such surfaces yet been detected? Are these objects rare, perhaps arising only in special circumstances in the early universe, or are they common but elusive, hidden behind appearances that so closely mimic black holes that current instruments cannot tell them apart? The answers are not known. For now, graver stars and related constructs occupy an intermediate status between pure mathematical curiosity and concrete astrophysical model. They demonstrate that in principle, the central singularity of a black hole can be removed and replaced by a more regular core without grossly contradicting observations. They also highlight how sensitive the structure of spacetime can be to the properties of vacuum energy and exotic matter. Whether nature actually implements any of these possibilities remains an open question, one that only more precise observations and a better understanding of high-density physics can resolve. In classical general relativity, the same equations that allow black hole solutions also admit other more exotic geometries. Among these are wormholes' hypothetical tunnels that connect distant regions of spacetime. A wormhole can be thought of as a shortcut where two locations that are far apart in ordinary spatial distance are linked by a path that passes through a curved interior region. Mathematically, such structures arise as particular solutions to Einstein's equations, sometimes by gluing together parts of different spacetimes along a throat. One well-known example is constructed by extending the solution for a non-rotating black hole to include a mirror copy of the exterior region. The result is a bridge between two asymptotically flat universes often called an Einstein-Rosen bridge. In the simplest form, however, this bridge is not traversable. Any object attempting to cross from one side to the other would find the throat collapsing too quickly, and signals would not make it through. To create a wormhole that remains open long enough for matter or information to pass, additional ingredients are needed. These typically take the form of exotic matter with negative effective energy density, which produces a repulsive gravitational effect. In the language of the field equations, such matter violates certain energy conditions that are usually assumed to hold for ordinary fluids and fields. Quantum effects can in principle generate small regions, where these conditions are violated, for example, in the Casimir effect between closely spaced conducting plates. However, engineering a stable macroscopic wormhole would require a sustained distribution of exotic matter far beyond any known physical mechanism. For this reason, traversable wormholes remain speculative. Their theoretical existence shows that general relativity does not in principle forbid spacetime from having non-trivial topology, but whether the necessary conditions are ever realized in nature is unclear. The connection between wormholes and black holes arises when one asks whether objects that look like black holes from the outside could in fact be entrances to such tunnels. In some theoretical constructions, the spacetime outside a wormhole mouth can mimic that of a black hole closely. The gravitational field at large distances the trajectories of orbiting bodies, and even the appearance of a dark central region surrounded by lensed light can resemble those produced by an event horizon. From far away, observers might interpret the object as a black hole. Only very close inspection of signal propagation near the throat would reveal differences. For example, light or particles that approach the mouth from certain angles might be transmitted to the other side rather than absorbed, and characteristic echoes or time delays could appear in the pattern of waves. In more elaborate models, the interior structure of a fuzzball or a gravastar could be connected to another region through a wormhole-like geometry, effectively turning a regularized black hole into a kind of gateway. In such scenarios, the singularity is removed, and information falling in could emerge elsewhere in the universe, or even in another branch of spacetime. This would provide a radical resolution of the information paradox not by storing or re-emitting information locally, but by relocating it. Whether such relocation counts as information loss from the perspective of a given region depends on how strictly one defines the relevant system. Another related concept is that of a white hole. A white hole is a time-reverse counterpart of a black hole. Whereas a black hole is defined as a region from which nothing can escape to the distant future, a white hole is defined as a region into which nothing can enter from the distant past. In simple extended solutions to Einstein's equations, a non-rotating black hole can be paired with a white hole through a shared throat. Matter may fall into the black hole region, and in the idealized extension emerge from the white hole region in another part of the spacetime diagram. In these constructions, the white hole expels matter and radiation, but never admits incoming material through its horizon. As with wormholes, the question is whether such entities can form under realistic conditions. The standard gravitational collapse of a star does not appear to produce a white hole. Instead, it leads to a black hole with a trapped region and a singularity. White hole regions in extended solutions are often interpreted as artifacts of the idealization, or as representing parts of the spacetime that are not physically realized in a collapse scenario. Nonetheless, the mathematical possibility of white holes has prompted speculation that some high-energy processes might create transient structures that briefly behave in a white hole-like fashion, emitting energetic outflows without obvious precursors. From the standpoint of black hole paradoxes, wormholes and white holes offer alternative ways to think about what happens to matter and information that approach regions of extreme curvature. If what appears externally as a black hole is secretly a wormhole mouth, then the infalling material does not encounter a singularity, but instead traverses a throat to another region. The information is not destroyed but displaced. If an interior singularity is replaced by a process that generates a burst of outgoing radiation, resembling a white hole phase, then information might be released back into the original universe in a highly scrambled form. Some regular black hole models incorporate this idea by allowing the collapsing core to bounce at high densities and then re-expand, turning what would have been a one-way in region into a transient in and out configuration. In such pictures, an external observer initially sees behavior close to that of a classical black hole, but after an extremely long time, small deviations accumulate and the object transitions into a different state emitting the stored information. The timescales involved can be very large compared with ordinary astrophysical processes, making direct observation unlikely, yet the principle that horizons are only approximate and temporary could relieve the strictest forms of the information paradox. At present, there is no direct empirical evidence for traversable wormholes or white holes. Observations of black hole candidates in X-rays, radio waves, and gravitational waves can be explained without invoking such structures. When mergers of compact objects are recorded, the ring-down phase matches the oscillation modes expected from black holes, with horizons and no clear signatures of reflection from a throat or of repeated echoes have been confirmed beyond statistical doubt. Images of supermassive black holes, such as those in the centers of the Milky Way and the galaxy M87, show photon rings and central shadows consistent with classical predictions. These results constrain the space of allowed alternatives but do not close it entirely. Many wormhole and regular black hole models can be tuned so that their external behavior aligns closely with that of standard black holes within current observational precision. Only as instruments become more sensitive and as more events are collected will it be possible to test for small deviations, such as slight shifts in ring-down frequencies, unexpected time delays in flares, or unusual patterns in high-resolution images. In the meantime, wormholes and white holes continue to serve as useful theoretical laboratories. They allow physicists to explore how spacetime might behave if topology changed exotic matter, or high-density phase transitions are permitted. They highlight the fact that the global structure of spacetime, not just local curvature, influences what is possible. A universe in which black hole-like objects are ends of world lines, where information disappears into singularities, looks different from a universe in which those apparent ends are gateways or turn into sources after a long delay. Each scenario carries implications for causality, for the arrow of time, and for the completeness of physical law. Even if traversable wormholes never exist in nature, understanding why they're forbidden or suppressed could shed light on deeper principles that make the observed universe coherent. Conversely, if future observations were to reveal even a hint that some compact objects are not simple black holes, but have internal structures or connections of the kind envisioned in these models, it would signal that the current picture of gravitational collapse is incomplete, and that space-time has layers of organization that are only now coming into view. While theory explores fuzzballs, gravastars, wormholes, and other speculative structures, observations continue to refine what is known about real black holes in the universe. Over the past few decades, a suite of instruments has transformed black holes from largely indirect concepts into objects with measurable properties. Among these instruments, gravitational wave observatories stand out as new tools that listen for ripples in spacetime produced by violent cosmic events. When two black holes orbit each other in a close binary, their motion generates gravitational waves that carry energy away, causing the orbit to shrink. In the final moments before collision, the frequency and amplitude of these waves rise in a characteristic chirp. After the merger, the remnant black hole settles into a stable state by emitting a series of damped oscillations known as ring-down. Detectors on Earth measure these subtle distortions in distance between suspended mirrors, and analysis of the signals reveals the masses and spins of the merging objects. The data collected so far show that many of the colliding systems consist of stellar mass black holes with masses ranging from a few to several tens of times that of the Sun, and in some cases higher. The waveforms match the predictions of general relativity for merging black holes with horizons and no solid surfaces. No clear anomalies have appeared that would demand departures from the classical picture, although the precision of current measurements leaves room for small deviations. At the other end of the spectrum, very long baseline interferometry and radio wavelengths has produced the first horizon-scale images of supermassive black holes. By linking radio dishes across continents, astronomers synthesize a virtual telescope with an effective aperture comparable to the diameter of Earth. This instrument, known as the Event Horizon Telescope, has observed the central black hole in the galaxy M87 and the one in the Milky Way Sagittarius A star. The resulting images show a bright lopsided ring of emission surrounding a darker central region. The ring arises from photons that skim near the unstable circular orbits around the black hole before escaping toward Earth, while the dark region corresponds roughly to the shadow where photons are captured. The diameter of the ring and the overall morphology align with relativistic simulations of accreting black holes. These observations provide direct evidence that compact objects in galactic centers have event horizon scale regions consistent with the presence of black holes. Yet, as with gravitational waves, the images also allow for certain alternatives such as regular black holes or very compact horizonless objects, as long as they reproduce the same near-field gravitational lensing to within current uncertainties. The next steps in observational work aim to increase both sensitivity and resolution. For gravitational waves, this means building additional detectors, improving noise suppression, and extending the frequency range that can be probed. Planned instruments on Earth and in space are expected to detect mergers involving intermediate mass black holes, and to trace the inspirals of compact objects into supermassive black holes. The latter signals, lasting for many orbits in strong gravitational fields, would encode detailed information about the spacetime geometry near the horizon, acting as precise tests for deviations from the Kerr solution of general relativity. For horizon-scale imaging proposals envision extending interferometry into space, placing radio antennas in orbit and combining their signals with those from ground-based dishes would create a baseline larger than Earth's diameter. Such a configuration could sharpen the view of photon rings, resolve smaller scale structures in accretion flows, and potentially detect secondary rings corresponding to light that orbits the black hole multiple times before escaping. These features are sensitive to the exact form of the gravitational potential near the horizon. Measuring them would offer a stringent test of whether astrophysical objects follow the standard black hole model, or whether small corrections from new physics alter the shape and brightness of the rings in measurable ways. Other observatories contribute complementary information. X-ray telescopes study the inner regions of accretion disks around stellar mass and supermassive black holes, where gas moves at a substantial fraction of the speed of light. The broadening and skewing of spectral lines from iron and other elements in these disks provide clues to the spin of the black hole and to the geometry of spacetime in the innermost stable orbits. High-energy observations of flares, jets, and coronae trace how magnetic fields and relativistic particles behave in extreme gravitational fields. Infrared instruments track the orbits of individual stars near galactic centers, refining estimates of central masses and allowing tests of relativistic precession. Together, these diverse measurements build a coherent picture in which black holes, as described by general relativity, are not only mathematically consistent constructs, but also real astrophysical entities with measurable properties. At the same time, they delineate the limits of current knowledge. Observations can probe spacetime down to a few times the horizon radius, but they cannot yet see inside. They can measure waveforms produced as black holes merge and ring down, but they do not directly reveal what, if anything, replaces the classical singularity. They can constrain how closely the external field matches the Kerr metric, but small departures perhaps caused by quantum effects may remain below detection thresholds. In this sense, data both confirm and leave open. They confirm that objects with horizon-scale regions behave externally as black holes are expected to behave. They leave open the question of whether the interior is singular, regular fuzzy layered, or connected to other regions. The paradoxes of singularities and information loss persist not because observations contradict general relativity, but because they highlight that a theory which works so well on large scales predicts its own breakdown in extreme regimes. As instrumentation improves, certain speculative models may be ruled out. If ring-down signals continue to match the pattern expected from classical black holes with increasing precision, and if no echoes or anomalies appear, graver star-like surfaces with strong reflective properties near the would-be horizon will become less plausible. If high-resolution imaging finds photon rings precisely where classical theory predicts, without distortions attributable to altered metrics, some regular black hole geometries will be constrained. If gravitational waves reveal that space-time around compact objects adheres closely to the Kerr geometry, then large deviations from standard black hole structure will be disfavored. On the other hand, any small but statistically robust departure from these expectations would carry great weight. A slight shift in the frequencies of ring-down modes, an unexpected time delay in a flare, an additional ring in an image, or an unusual pattern in a long-in-spiral waveform could hint at new phenomena near the horizon. Such anomalies would need careful scrutiny to rule out mundane astrophysical explanations, but if they persist, they would offer precious clues about how gravity behaves beyond the regime where general relativity has been tested so far. The interplay between theory and observation in this area is therefore subtle. Theoretical work ranges from conservative extensions of general relativity with regular cores to radical reimaginings in which spacetime contains tunnels, bounces, or holographic surfaces storing quantum information. Observations for now draw a frame within which these ideas must fit. Black holes must exist with certain masses, spins, and accretion properties. They must merge in ways that produce gravitational waves of measured shape. They must cast shadows of observed size in surrounding emission. Any successful theory of quantum gravity and black hole interiors must reproduce these facts while also addressing the unresolved paradoxes. In this light, the black hole paradox can be seen less as a problem and more as a guidepost. It points toward a domain where the smooth geometry of general relativity and the probabilistic rules of quantum theory both play essential roles, and where neither by itself is sufficient. Sagittarius. A star-distant quasars merging stellar remnants and hypothetical primordial shadows all participate in this story. Each black hole, real or speculative, marks a boundary where current understanding of space-time and information is stretched. The question of what truly lies at the centres of these objects and of how the universe keeps track of every bit of information that falls in remains open. Future telescopes, detectors, and theoretical advances will narrow the possibilities, but it is unlikely that the final answer will be simple. The same equations that predicted black holes as strange mathematical curiosities now describe engines that shape galaxies and light up the distant universe. The paradox that haunts modern physics is that these engines, so well described from the outside, still hide an interior story that has not yet been written in full.